Homework 5, exercise 4, we're going to solve in two different ways. So we're measuring this radiation with a Geiger counter. Geiger counter clicks on average 3.2 times per second. We start a stopwatch. What's the probability that the Geiger counter clicks in the 1 second interval between 5 and 6 seconds? So one of the key observations here is there's sort of nothing special about 5 and 6 seconds. It's just a 1 second window. So I could have changed this to any 1 second window. 1 second window. And the first way that I want to solve this problem is with a Poisson distribution. The Poisson distribution, we could say, okay, well, in a 1 second window, how many clicks do we expect? Geiger counters kind of are clue in that, though we're modeling this with a Poisson distribution. In a 1 second window, how many clicks do we expect? Well, we expect 3.2. So the probability that our number of clicks in that interval, maybe I'll write this like 5 to 6, that interval 5 to 6 is greater than or equal to 1. Well, that's just the probability it clicks once or twice or 3 times or 4 times or 5 times or 1 trillion times in that interval, whatever amount of times. And so let's introduce a random variable x. Let's say x is the number of clicks in the interval. Well, then x is going to be distributed like Poisson 3.2. Because that's the number of clicks we expect in the interval. Okay? We're using this Poisson assumption. Okay, and so what's this? This is just the probability that x is greater than or equal to 1, which, okay, we could either write as maybe the sum as I equals 1 to infinity of the PMF of x of I, or something. That's the correct answer. But this is actually just going to be equal to 1 minus the probability that x clicks less than 1 time, which means it clicks 0 times. And since we have this Poisson distribution to work with, this is an easy thing to compute. This is just 1 minus the PMF of x0, which is going to be 1 minus our lambda. We actually aren't even going to care what the lambda is for right here, because that just goes to 1 of e to the minus lambda. Okay, and this thing is going to be quite close to 1. Let me see if I can get my phone to do this one. I don't know if it will. 3 minus 3.2, and we want to do e to that power. And so I get this as a 90. The probability of a click in that 1 second window is about 0.959. Okay, it's quite likely that there will be a click in that window. Let's look at it the other way. 2, let's look at it as an exponential distribution. Okay, so y is going to be distributed exponential, also with that parameter 3.2. And what's the story for y? What's y going to be? We think about it this way. We start a stopwatch at 5:00, at the 5 second mark. I guess we're calling this 5.00. And stop it when we hear a click. Then y is the time on the stopwatch, on the stopped stopwatch. after that, after we've stopped it because of the click. Okay, so the probability that that the Geiger counter clicks in this 1 second interval is equal to the probability that y is less than or equal to 1. Right? Because if we stop our stopwatch in less than a second after 5, well, then we've sort of clicked between 5 and 6. So this is the duality argument. And what's this? This is the integral from where we start, which is 0 is the smallest thing y could be, or the smallest thing an exponential distribution is going to be, to 1. This is the same 1 of that exponential distribution, which is going to be 3.2 e to the minus 3.2 t dt. Okay, and now we can integrate this thing. What happens if we integrate this? Well, we're going to get a 3.2 out here, and then this integral is going to be e to the negative 3.2t divided by negative 3.2, right? And then it's going to be evaluated at t equals 0 and t equals 1. Okay, and we get some cancellation here. So this is going to be e to the negative 3.2 times 0, which of course is just 1, minus e to the negative 3.2 times 1, which of course is just e to the negative 3.2, right? And so that's equal to the same thing that we got above. That was equal to this 1 minus 1 times e to the negative 3.2, this 9.59. Cool. Okay, so these are two different perspectives, and this is that again, one more illustration of that exponential Poisson duality, which is that we can kind of get from one to the other, or in lots of problems we can choose which way we want to look at the problem to decide whether we want to use a Poisson distribution, which is going to count the number of something, or an exponential distribution, which is going to say when something happens.